Good afternoon. It's so nice to see so many people who are interested in our topic today, or who are relatives of Matt or old Matt. This is a terrific turnout. I'm Bruce Bidgood. I'm the acting chair here at the Northwest Regional Campus. And our discussion today, Matt says all you have to do is get a catchy title. So, Glaciers, Streams, and Salmon, and will climate change affect the levels of water we have here in our rivers? As a biography, I've known Matt for a number of years, since he was a doctoral student and then doing his postdoc here. He was born in Juneau, Alaska. Just leave that for a pause for a moment, and then migrated here.
I apologize.
I wasn't going to say anything. I'll leave it to you. And he did finish his degree at UNBC. He currently serves as an adjunct faculty member here at UNBC in the Sciences Department, geography most specifically, and also serves as a professor of geography at Northwest Community College. So just before I release it, I must apologize. I have to run for another meeting online. But I also, before I returned it over to Matt, wanted to just make people aware of, for the first time ever at UNBC and at our campus here, most specifically, we're going to have an Elder in Residence. And the Elder in Residence program is something that comes out of our First Nations Studies Department and our Aboriginal Services Plan. It involves having one of the local elders come here to our campus and be available to go to classes and to meet with students and faculty members. In addition, what we've done is schedule a series of 4 meetings every Wednesday in April, every Wednesday at noon. And our candidate is Mr. Mel Bevan. Mel Bevan is a hereditary chief of the Kitsillas First Nation. He has been involved in the leadership of Kitsillas before there was a reserve on Queensway. I understand he cleared the first trees and is still, to this day, a modern-day treaty negotiator for both Kitsillas and Kitsumkalum. So I would suggest to you that please feel free. There will be posters all around town, and in fact, there's going to be some delivered to you during this meeting. If you would like to attend, please do so. If you would like a private audience with Mel, who has, he's been around for as long as the hills. He has stories that go back as far as the Kitsillas people were here. Feel free to contact us. We'll make that happen. So once again, thank you all, everybody, for coming here today. I apologize for my departure, and Dr. Ice, as I affectionately refer to him, will talk to you about glaciers and its impact on our local rivers and fish. Thank you.
Awesome. Thank you very much, Bruce, and thank you all for coming. I'd like to start by acknowledging the Tsimshian people of Kitsumkalum, and especially the Lakskiboo clan on whose traditional territory we're gathered today. And furthermore, I'd like to start by saying that this talk is about a research collaborative as much as it is about glaciers and streams and salmon in particular. So the research I'm presenting here is guided by and led by Kitsumkalum. It's of the Kitsumkalum traditional territory, and the main purpose is to inform the Kitsumkalum community of possible benefits moving forward and also risks and how to adapt to those moving forward. And as a teacher, perhaps the thing I'm most excited about is the opportunities that this research effort provides for students, both here at the university and at the college and at Kitsumkalum, with cool experiences to get out and study our big backyard, essentially. So I'm not the only person involved with this. We have a really big group of people, and it's growing all the time. Again, it's really led by Kitsumkalum. So Mark Biaggi, in particular, the Kitsumkalum Fish and Wildlife Operations Manager, Warren Bolton, the GIS technician at Kitsumkalum, Rob Connolly, the Fisheries Administrator, are all individuals who've been involved in this from the get-go. Also Brian Menounos at UNBC in Prince George, Catherine White, Gordon Wary at Northwest Community College, and tons of NWCC students. We've been able to bring some of this science into our field schools, and a lot of you are here today. Could you raise your hand if you've been involved with this? A number of you, so you can ask them really hard questions after the talk as well. It's been really fun to involve all of you in this work. I'd like to also point out at the outset that we've been fortunate over the last year to receive funding from the Indigenous and Northern Affairs Canada. Funding for First Nations to partner with other local institutions specifically for climate change research purposes. So something we're really excited about, and hopeful we'll receive funding moving forward in future years. So in fall of 2015, Mark Biaggi, the Fisheries and Wildlife Manager at Kitsumkalum, came up to the college and met over coffee with Gordon Wary and Catherine White and myself, and pitched this idea of doing research in and of the Kitsumkalum traditional territory. And the main question is this: how will climate change impact food security? Right? That's the primary question. Here we have an awesome picture of fish. Of course, fish aren't the only ingredient for food security, but they're definitely a cornerstone for the Kitsumkalum community, also for us in the Northwest at large. Right? Super important. As well, since I'm a glacier nerd, Mark asked me this question: how fast are our glaciers melting, and does that matter for salmon? And so that was really the jumping off point for this back in the fall of 2015. Since then, we've started monitoring stream temperatures. We've started studying the glaciers of Kitsumkalum and starting looking at seasonal snowpack as well, how that impacts streams and salmon, and that's what I'm going to present to you today. I'm going to start with the glacier picture, my focus, where I'm coming from, and move into snow and then into stream flow and stream temperature. So at the outset, this is the subtitle of my talk, but I should really probably change it because the focus is going to be on salmon, really. Is climate change going to leave the salmon of Kitsumkalum River high and dry? All right. But when it comes to salmon, it's really critical to note that there are so many things that impact salmon. They have such an amazing life cycle, from the freshwater environment out to the ocean and back again. And there's a whole host of things that impact salmon. A multitude of things, and it's really hard to understand and try to pick apart what are the key players. And in reality, it's all of these things combined, some more than others. We're going to be focusing today on climate change, and really only a little part of climate change. Greg Knox gave a really great talk back in November that summarized the impacts of climate change on the Skeena River at large. Really highly recommend that talk if you haven't seen it yet. It's available online. Does a great job at summarizing all the potential impacts of climate change. Today we're just going to focus on the Kitsumkalum watershed and look mostly at the impacts to the freshwater environment, or only to the freshwater environment, particularly to stream temperature and stream flow volumes. A little bit of a summary at the outset. Why are we concerned? What are some of the big concerns for climate change impacts on salmon? And some of these were in Greg's talk in November, and some of them weren't covered, but are critical for understanding potential impacts in the Kitsumkalum and other local watersheds. So first, a bit of optimism. There are a lot of studies out there that show that salmon populations have incredible resilience, all right? And should have the capacity to respond to change if the magnitude of that change and if the rate of that change isn't too great, right? And that's really key. There's lots of information that shows that salmon are resilient, but we have to give them a leg up to be able to do so. Second, there's likely increases in thermal stress. And it's really key here to remember that they're all different parts of the salmon life cycle. So different temperatures are important at different times of a salmon life cycle. So spawning migration, spawning, rearing, smolt migration, all of these different times in a salmon's life cycle have different thermal requirements. But it's likely to have increased thermal stress moving forward with climate change. In addition to increased warming, we give the competitive edge to these warm water predators, particularly that consume smolt on their migration. So if we move to a new, warmer thermal regime, we give the advantage to more warm water fish that might prey on salmon smolt. Right? The hypothesis is that the impacts will be felt more greatly for the stocks that spend at least one summer in freshwater. Right? Particularly sockeye, coho, and chinook. So you have greater exposure to that thermal stress, since they're living for a longer time in that freshwater environment. But also, a potential positive, some studies have shown that you might have increased aquatic food web productivity. You might actually get some growth response with warmer conditions in some watersheds. All right. We're worried about reductions in volume of late summer and early fall flows. And this is really critical for spawning habitat, for access to spawning habitat. There's a potential for an increase in intensity and frequency of winter flooding. And this really gets to, as our winters warm, we have more rain on snow events and more snowfall or precipitation that used to fall as snowfall now falling as liquid water. Typically, snow falls in our mountains and it's stored until the springtime. With warmer temperatures, however, we have a likelihood of increased winter flooding events. And these potentially lead to egg scouring in the riverbeds. Also, reduced availability of slow water habitats. These flooding events tend to make these slow water habitats less accessible, and you can get displacement of juvenile salmon without these slow water habitats. And finally, the last one I'll list up here is seaward migration timing of smolts is timed with the peak of snowmelt. They've adapted, they've evolved to time this migration with the peak of snowmelt. If our peak snowmelt changes, how then does that impact smolt as they arrive out in the marine estuaries? So a number of things to keep in mind as we move forward with this talk. Some critical things for salmon with climate change. All right, so starting with the big picture, this map on the left, this is a map of the Pacific coastal temperate rainforest that extends from northern California all the way up to southern Alaska. And we're pretty much smack dab in the middle of that. All right, phenomenal ecozone on our planet, huge biomass, super important. There have been a number of studies already that have done similar work, looking at the effects of climate change on stream temperatures and on salmon. So in Washington State, this was a really comprehensive study published in 2010 by Nathan Mantua, and they concluded that many streams already have periods with episodes of extreme thermal stress for salmon. So already, this is meaning this was published in 2010, so this is data probably from the early 2000s. There will be large increases in the number of stations that are especially unfavorable for salmon in summer. And that T sub W, that's weekly average temperature. So an average weekly temperature of greater than 21 degrees C. So in Washington, they're already finding times of critical thermal stress for salmon and the likelihood of that to go warmer. Juxtapose that against Juneau, Alaska, my hometown. This was a study done by Jason Fellman looking at the impact specifically of glaciers in local watersheds. And they found that temperatures in heavily glaciated watersheds were predominantly below the optimal thermal range for salmon, and actually concluded that warming and loss of glaciers will actually improve conditions for salmon. So in these really heavily glaciarized environments, and in this case you're talking glacier cover of up to 65% of a watershed, so massive amounts of ice, the conditions are actually suboptimal for salmon, and that climate change will actually enhance conditions. So the big question here is, where are we, right? We're somewhere in between these two. How bad or good is it? All right, a little bit of the glacial and climate bigger picture of where we reside here in British Columbia. So this is BC. All of the light blue here are all glacier cover. About 17,000 glaciers in the province, 25,000 square kilometers of ice. I want to point out here and focus in mostly on the coast mountains. So the southern coast mountains and the big ice fields here north of Vancouver, the central coast where we are, and the big ice fields in the northern coast mountains. And the critical thing I want to point out is that we've got really big ice fields down here, really big ice fields up here, and where we live in the central coast, much smaller glaciers. Our mountains are generally lower elevation, and we don't have the massive amounts of ice as elsewhere in the province. This is a plot showing all of the glaciers in the coast mountains as black dots, organized by latitude on the x-axis, so south here, north over there, and then this is your median glacier elevation. What this is showing is that in their southern coast mountains, we have a lot of glaciers that are at much higher elevations. Right? They're further south in a warmer environment, but they're going to be a bit more resilient to climate change because they're at such a higher elevation. The glaciers to the north of us are in a cooler climate and similar elevation, perhaps slightly a little bit higher than where we are. This is the Central Coast Mountains here, essentially from Bella Coola up through the Nass, and then the blue dots are the Kitsumkalum glaciers. So generally, smaller glaciers at lower elevations and a bit more vulnerable to climate change. This is from Tobias Bolch's work from 2010 with others at UNBC, showing how all of the glaciers in BC have changed from 1985 to 2005. And what he does here is break up each of these regions and show a change in surface area in terms of percent per year. The main takeaway here is to look at the Central Coast Mountains where we are. And it has the highest rate of recession of glacier melt of anywhere in the province. Right? The average for BC is minus about 0.5% per year, whereas here it's more than double that. All right? So that lower elevation ice is more vulnerable. We're already seeing it recede faster, and it's likely to recede faster moving forward. All right, zooming in on the Skeena watershed. So this is where we live. Terrace is down here. When we look at a watershed and we look at glacier importance, the critical thing is percent glacier cover. How much of that surface area of that watershed is covered by glacier ice? And the Skeena doesn't have a lot if you look at the entirety of the watershed. So back in 1985, we had 972 square kilometers of ice, which was 1.8% of the whole Skeena watershed. To 2005, it shrunk a bit and went down to 1.5%. So all told, if all the glaciers in the Skeena watershed melted, it wouldn't be a massive impact on the Skeena watershed writ large. However, if we zoom in on a number of the subbasins, the smaller drainages, there are streams and rivers within the Skeena watershed that are really critical. They have much more glacier cover, and they're bound to be more impacted by climate change and the loss of glacier ice. And so 4 watersheds, some of the 4 closest to us, comprise nearly 50% of all the glacier ice in the Skeena watershed. So when it comes to glaciers and glacier change in the Skeena watershed, impacts on the watersheds near us are of primary importance. All right, so this is starting to get down into Kitsumkalum glaciers. Right? On the left here is a little animation. That is a 2017 satellite image, so that's from last summer. These are some of the glaciers at the headwaters of the Beaver or Upper Kalum River. And you see some outlines from 85, 2005, 2017 for these glaciers. From this freely available satellite imagery, we're able to map all of the glaciers and see how they're changing through time. So for the Kitsumkalum watershed as a whole, we've gone from about 8.1% glacier coverage in 1985 down to 5.6% glacier cover in 2017. So still quite a bit of glacier ice, but it is dwindling. Right. Some more stats on the glacier change within Kitsumkalum. So again, these are for these 2 periods, 1985 to 2005, then 2005 to 2017, and then for the entirety of the period. And the key things I want you to get from this are, first, since 1985, Kitsumkalum ice, Kitsumkalum glaciers have receded by 30%, 31%. We've lost 30% of the glacier ice within Kitsumkalum watershed since 1985. And the rate of change for that first period was about 0.9% per year, and it seems to have increased for the period 2005 to present day. Right? So losing about 1% or so of our surface area per year. So we're losing that ice, we're losing it quite rapidly. All right, so we're going to zoom in now, and that was the Kitsumkalum watershed as a whole, and now we're going to look at some of the sub-basins, the sub-drainages within the Kitsumkalum watershed. And as a bit of an introduction to some of these drainages we're going to talk about, I want to go around these here. So for orientation, we are down here. Terrace is right about down there. Right? Here's Kalum Lake right here. The highway heads north up to the Nass through this way. Right? We're going to look at the Beaver River in green here. That's where most of the glaciers are in the Kitsumkalum watershed, 13% glacier covered. Mean elevation of that basin is about 1,090. Moving our way around, the Cedar up here has the least amount of glacier cover at under 1%, about 0.6% glacier cover in the Cedar. Wasatch Creek over here, a smaller drainage on the east, 1.3% glacier cover. Goat Creek, 3.3% glacier cover, another small basin on the east. And then down here in the southwest, we've got the Nelson here in purple and Star Creek, two other basins that have quite a bit of glacier cover. So the Nelson with 10.4% glacier cover and the Star watershed with 7.9% glacier cover. We've also looked at stream temperature in some of the aggregate whole of some of these. So what we've done is we have stream temperature for the lake. And so for the entirety of the watershed that feeds into the lake, we've got 1.3% glacier cover. And for everything that feeds into where our stream temperature sensor is down here near the outlet of Kalum River is about 6.1% glacier cover. All right. So within the larger watershed of Kitsumkalum, we have these other sub-drainages that are also going to be responding in unique ways to climate change. Moving forward with this talk, the critical thing here is to recognize when glaciers are important in the annual hydrograph, in the year when water's coming off our mountains. So this is adapted from really one of the first papers that looked at the response of stream temperatures and stream volumes to glacier change back in 1985. These two plots show percent annual runoff for every month from October through September. This scenario here is for a watershed with 14% glacier cover. This one is 0% glacier cover. And the main takeaway is what happens in late summer and early fall, specifically July, August, and September. You go from high flows, because your glaciers are melting and contributing to your rivers and streams, to really low flows. You don't have ice to melt at that time of year when you've lost those glaciers. The seasonal snowpack is gone. It's generally a dry time of year for us, and that ice then is gone. And so our flows in late summer and early fall are low. All right. One thing that's really important to also study and that we're working on is looking at glacier surface elevation and volume change. So the previous figures showed just surface area. If you're in a satellite looking down at a glacier and you map its surface area and then you map it again and difference it, you can get surface area change. This is looking at surface elevation change or a total volume change. This is a digital representation of the largest glacier in the Kalum watershed. This is at the headwaters of the Beaver or Upper Kalum River. The outline of the glacier looks like that in blue. This was created last summer from LiDAR or a laser scanning flight. Essentially you have a plane flying over a surface, shooting a laser beam down, you get a reflectance, and you can map in great detail the surface. You can then difference that surface from other previous surfaces that have been mapped before, right, and get a total volume change. So the colors here represent how much surface elevation change there's been on this glacier since 1999. The darkest red colors are more than 30 meters of melt vertically. These orange colors are between 30 and 20, and this yellow area is between 10 and 20. So lots of downwasting, we call it, lots of surface melt. The numbers on this here, so from 1888 to 1999 and from 1999 to 2017, on average we're losing about half a meter. If you average this change over the entire glacier, we're losing about half a meter of thickness in terms of liquid water every year. That yearly discharge, that yearly melt comes down our rivers typically in July, August, and September. And the volumes on average for these periods are these. So from 88 to 99, averaged about 9 million meters cubed. And from 99 to 2017, slightly less, about 7.6 million meters cubed. And for reference, the average daily discharge of Kitsumkalum River, the average amount of water coming out of the Kitsumkalum on any given day is about 10 million meters cubed. So from this one glacier, it is the largest glacier in the watershed, but from this one glacier, we have the equivalent of one entire day of water coming out of the Kitsumkalum River, coming off of this glacier each year. Right. So one project we're working with is doing more of this differencing, this elevation model differencing. And to do so, we either need to hire pilots to go and fly and get us more laser scanning imagery, or we can start to do it ourselves. And part of the grant we've received is to do some of this ourselves, get some tools to do this ourselves. And so these are folks involved with the project. This is Warren Bolton and Julia Roberts and Jim Webb and Mark Biaggi, and then a trainer from Spatial Technologies, Mr. John Tong. And they're doing a training. We did a 3-day training back in March to learn how to use this really fanciest surveying drone on the planet today. It's about a $70,000 surveying drone, and a really phenomenal tool for looking at how landscapes change. So one thing we're going to start to apply this summer to look more closely at how the volumes of these glaciers are changing and how much water is coming off them and contributing to our streams. From this, we produce models such as this. This one was done by a smaller personal drone, but this is a surface representation of the small glacier on the north side of Maroon Mountain. And the plan is, moving forward, to every summer get to a number of these glaciers and be able to, in detail, measure how much water is coming off of these glaciers. How much volume change do we have every year? Right. So how important are the glaciers of Kitsumkalum as a whole? This is a picture from January. This is the hydrology class. Some of you in the room are in this picture. We're measuring discharge, in this case, of Shames River, so seeing how much water is coming out. So in terms of the Kitsumkalum and the subdrainages within it, how important is this glacier melt? How much of that, in terms of percent, how much of that water coming off in July, August, and September is from glacier melt? And this is kind of back of the envelope estimates at this point. We hope to get this in more detail. But in general, for that earlier period when we had more glaciers, so back in 1985, we had up to about 12% or so in some of the basins with the most glaciers. About 12% of that water coming out of the river is probably from glacier melt. As we lose that ice again, that contribution to the flows decreases. And so to this summer, about 9%. And again, this is in an average year. It's important to know that in a really hot year, in a really hot, dry year, glacier melt becomes more important. And these numbers are likely to double. So I would estimate in a hot, dry year, probably up to 25% or flow of that, or 25% of that flow coming out of the river is likely from glacier melt in a hot, dry year. Right. This is the story for glaciers moving forward, and it's not a good one. The general picture for glaciers worldwide looks like this. This is from a study looking at all of Western Canada's glaciers done by Gary Clark and others, published a couple of years ago. And these two plots show, this is for the coast mountains. This is for the interior mountains of Western Canada, 1980 to 2100. Each of the colorful lines are emission scenarios or representative concentration pathways. Essentially, they're whether we get our act together with regards to carbon emissions or not. Okay? The red line means business as usual. We keep emitting as we are today. The blue line is the most optimistic, that we really get our act together and we start to curb emissions now. The other two lines are more middle of the road, that we delay a little bit. It takes us a little bit of time to start getting these emissions down. Regardless of emission scenario, regardless of whether we get our act together or not, we're going to lose the vast bulk of the ice in our mountains by 2100. Okay. Again, note that this is for the coast mountains. It's a little bit better picture than for the interior mountains. Part of it is that this is in a wetter climate. Another thing I'd note, though, that this is for the entirety of the coast mountains, so including all of the big higher elevation glaciers to the south and to the north of us. We here in the Central Coast, the glaciers here are likely a bit more vulnerable. I would argue that these curves are a bit steeper for us here in the Central Coast. So the takeaway there is the ice in our mountains is leaving us, and it's going fast. Another thing we're looking at is the role of seasonal snowpack and snowmelt. So glaciers are one part of the equation. We get a lot of snow here. Snowmelt is critical. This is Julia Roberts, NWCC student and Kitsumkalum. She'll be our first glacier studies intern at Kitsumkalum. We're really excited about. She's going to be working with us this summer. This is her up in the Shames watershed this winter, measuring snow water equivalent of the snowpack up in Shames. And so the amount of snow that we get in the winter and is then stored for release in the spring and early summer is really critical for flow volumes and temperatures as well. And one thing we've started to do is use remote sensing to look at how the snow cover area changes with time and how that impacts stream flows and stream temperature. So we've done some mapping of snow cover using the MODIS instrument, which is on NASA's Terra and Aqua satellites. MODIS is really nice in that you get a picture of every spot on Earth between 1 and 2 days. The bad parts are the resolution's not fantastic, but your chances of getting an image of your area of interest that doesn't have clouds in it is increased because you have a shot every single day or almost every single day. So from those pictures, this is from 2017. This is this past summer. We got good imagery April 6th, May 25th, June 23rd, and July 19th. So not a whole lot of cloud-free images, but some to be able to map how seasonal snowpack changes with time. We're starting to look at this for each of the individual sub-drainages within the Kitsumkalum to see how snowpack influences stream flow. One first takeaway is comparing the 2 years, so 2016 to 2017 when we have this data. Remember that in March 2016 we had those record-setting temperatures, it was plus 20, really warm in late March. That led to a really rapid melt of the snowpack in 2016. And so by late May in both of these years, this past summer had about 35% more snowpack, more snow cover area than in 2016. So the temperature each spring really has a big impact on how much snow there is available to contribute to these streams. And we're starting to get a handle of what that looks like. And one of the main takeaways from this, looking at all the smaller sub-drainages, is that there's a relationship indeed between snow cover percent in your basin, how much snow cover is covering your basin from 0% all the way out to 100%, and your weekly average temperature of your stream. And one thing that we're finding in both years, regardless of the timing of when that percent coverage is reached, is that about 35% snow cover, you start to see the increase in stream temperature. And really before that, stream temperature is kind of insensitive to warming. Right? So we get warming going on in the early spring, but stream temperatures stay below about 8 degrees C or so until you get below 30% snow cover, and then it seems like your stream temperatures start to go up. All right, so moving on to the main part of our research, which is looking at the thermal characteristics, the temperature characteristics of the streams in the Kitsumkalum watershed. And so this was really a big sub-question. What is the thermal regime of Kitsumkalum River? Another NWCC student, Dallas Nickel, in one of our first efforts to go out and measure stream temperatures around the Kitsumkalum watershed. So a bit of our methods. This is adapted from the same study that was done up in Juneau that I talked about earlier. I talked to Jason Feldman and looked at all the methods that they used, and we employed the same things here. We're measuring stream temperature with these little teeny temperature sensors. We're measuring stream temperature every 15 minutes. So they're out in the stream, measuring a stream temperature every 15 minutes throughout the summer. We put them in about early May, and we've left them in through October for both 2016 and 2017. This is what the setup looks like with some of the students deploying one of the first ones. So we have a little bit of a coated cable anchored to a tree going down to a chain which serves as the weight, which holds this little PVC housing to protect the sensor. So if you've seen any of these in the streams, that's what those are. We have a little sign there that talks about it too, but that's the basic setup. Put them in there, and they record temperature every 15 minutes for the entire summer. All right, so what we did is we put them in 8 different locations. We've got one here down near the mouth of the Kitsumkalum looking at stream temperature of the river. We've got one here for Star Creek. We've got one here for Nelson. We've got one here right off of the Hart Farm, but it's actually in the lake, measuring lake temperature. We've got one across the lake here measuring Goat Creek temperature. One here measuring temperature of the Beaver. One a bit further north measuring the Cedar. And then one over here on Wasatch Creek. And this is what we start to get. So this is for 2016, and as a bit of context, 2016 was a nice summer. If you remember 2016, it was the 14th warmest May to October period on record, about a degree colder than the long-term, or excuse me, a degree warmer than the long-term average. It was also the 4th driest May to October on record. That was a nice summer, if you remember that one. And so in general, we got higher stream temperatures than in 2016, which you'll see in a minute. So this plot's May to November. On the x-axis here, we've got weekly average temperature. And in all these plots, every temperature I'm going to show you is a weekly average temperature, a very common metric for looking at impacts to salmon of stream temperature. Each one of these colored plots is for a different subdrainage in the Kitsumkalum. And then down here in black, this is your air temperature, your weekly average air temperature for the summer. A couple of things stand out. One is there's a lot of variability. We have some streams that stay cold, others get quite a bit warm. You'll also note that it pretty well mirrors air temperature. So you can see these peaks pretty well line up with stream temperature peaks. A couple things to point out of things going on in this slide. So the top two, the ones that get the warmest, the blue line and the purple line. The blue line here on the top, that's Kalum River, right down near the mouth. And then the purple one there is Kalum Lake. And those two are doing something different. And that's due to the ability of the lake to warm up. So big, broad, flat area. The water is resident there for a long time. It can warm up much more than a moving stream. So the lake is having a huge effect on the river and the lake itself, obviously. And they're kind of doing their own thing. They warm up more, and they're not necessarily in sync with the other streams. All the other streams kind of relate to what's going on with the glacier cover, except for Goat Creek. Goat Creek is in orange here, and it's significantly colder than most of the rest. And Goat Creek doesn't have the most glacier cover in it. We'll talk about why Goat Creek is unique in a minute. If anyone's familiar with Goat Creek, it's this east-west drainage with really steep sides. And my hypothesis here is that it doesn't get much, if at all, any incoming solar radiation, or very little in shadow most of the summer. But it's unique. It's doing something totally different. It's much colder. Everything else kind of goes by glacier cover. So down here we've got blue and green. Those are the Nelson and Beaver rivers, which have more glacier cover. Star Creek, Wasatch, and then up to the Cedar with very little glacier cover being the warmest. This is what it looked like for this last year. I'll flip back and forth just so you can get an idea of the difference. Definitely a bit of difference going on. The same general pattern, though, however, persists in terms of Goat Creek being the lowest, the two lake-influenced temperature sensors being the warmest. Last summer was not as nice a summer, if you remember. It was colder than average. Not terribly so, but a bit colder than average. However, it was the 4th wettest May to October on record. Last summer was a wet summer. And this definitely had an influence. So generally these curves are cooler. You do see, however, this big spike midsummer. If anyone remembers, that was about riverboat days. It was really warm for a good week, 10 days or so. And you see all the streams responding to that and going up significantly. All right, I'm going to talk next about temperature thresholds. So of these temperatures that we've just looked at here, which levels are critical? Why do we care about some of these certain temperatures? And this is a grab bag of some of the published values that are in lots of different peer-reviewed articles about what critical temperatures there are. So some talk about a lower threshold. So this one's saying 5 degrees C is kind of a lower threshold. We don't have a lot of bioproductivity at that cold or colder, and so it's not a great environment for salmon. Surprisingly, some of the most stringent criteria that I found were from the State of Washington Department of Energy. So they have a 14.5 degree criterion for spawning, rearing, and migration. It's Department of Energy because they're really concerned with releasing enough water from dams for keeping water at a certain temperature. This study, greater than 15% increased predation, competitive disadvantages above that temperature. 21 to 22 degrees, you're getting up to temperatures that prevent migration, right? 21 degrees, susceptible to disease, prolonged exposure, lethal to juveniles and adults. Getting higher, this is really the max temperature I've found in the peer-reviewed literature. Studies showing cardiac failure threshold of about 24.5 degrees for Chinook. Salmon they can't function above that temperature. And then other studies look at an optimum range for growth. Some have identified different ranges between 12 and 14, others 10 to 18, looking at what's an optimal range for salmon. And so if we plot these against 2016, this is what it looks like. So again, same plot from 2016. The y-axis is extended a bit so we can fit all those on there. And the main takeaway here is that we're at a pretty good space right now with respect to temperature in the Kitsumkalum. All right, we're starting to get up towards some of these onsets of thermal stress for a limited part of time in a couple watersheds. So in parts of the lake, in parts of the main river. We're getting close there in the Cedar River as well. Right? We're definitely not getting up into these other critical temperatures where you have reaching the upper bounds of a species assemblage threshold or a migration barrier or indeed cardiac failure. Right, so we're in a good place with respect to temperature, at least at the moment. Right? However, what's going to happen moving forward? This is from a paper by Connell and Shanley looking at this Pacific coastal temperate rainforest and how temperatures are likely to change out to 2080. And the big takeaway here is that we're going to see a lot of warming, anywhere between 3.2 and 6.5 degrees C of warming by 2080. So what does that mean? What does that mean for stream temperature? What does it mean for melting snow? What does it mean for loss of our glaciers? And so what I've done here is I've done a kind of a pretty simple first order model of what temperatures, what max weekly average temperatures are likely to be under these two scenarios. So again, these dots here plot maximum weekly average temperature for the different streams. The color corresponds here. So orange to orange for Goat Creek, et cetera, moving up. And these two RCP 4.5 and 8.5, those again are the two emission scenarios that are used in the Colin Shanley report. So again, 4.5 is kind of middle of the road. We start to get our act together by 2040, reducing emissions. RCP 8.5 is we don't get our act together at all. The takeaway here is we start to move up into these areas of increased thermal stress moving towards 2080. So we're not getting up towards the migration barrier or the cardiac failure, but definitely moving into this onset of thermal stress as we move towards 2080. So impacts to salmon definitely as we move forward. All right, so getting back to my primary question, which was the title of my talk, and some takeaway messages. Will climate change leave the Kitsumkalum River high and dry? First, Kitsumkalum watershed conditions at present, so today, in today's climate, they likely don't present much, if any, thermal stress to salmon. We're in a pretty good place right now. The conditions are good for salmon. Right? That's a good, definitely a positive. Right? However, summer water temperatures are likely to increase by at least 2 degrees C by 2080. So in all our watersheds, they're likely to increase by at least 2 degrees. Average July, August, September discharge is likely to decrease by up to 12% by 2080 as we lose those glaciers. I would argue that that would probably be a bit more, given that 12% is for an average year, not a max year for glacier contributions. And then next steps for our work, our collaborative, are to first, this summer we're going to start seasonal glacier mass balance monitoring. So that largest glacier in the Kitsumkalum, we're going to actually fly up there in about 1 month and start studying that glacier in detail. Also studying some of the other smaller local glaciers like the one on the north side of Maroon Mountain that we can hike to pretty readily. We're going to continue and enhance our stream monitoring. We're hoping to launch weather stations, so other meteorological monitoring stations around the watershed. So all the temperature data I gave you, that's from the Terrace Airport. Obviously around the watershed in the larger region, we have a lot of spatial variability. So trying to start to understand that. And then really main goal is to train and inspire our leaders here in the Northwest. So I'll stop there and let you ask any questions. Yeah.
You talked about the salmon being extremely adaptable. How likely is it that some of that adaptation could take place to mitigate some of the danger?
In terms of us mitigating?
No, this is just the salmon adapting
Yeah.
in a warmer temperature.
Yeah, so there were some cool studies. So that one study I pointed to where it pointed to a maximum threshold for Chinook of 24.5. What they did is they took young Chinook and they raised them at present day water temperatures, and then they raised them at +4 degrees water temperatures and then see how they responded. And their kind of optimal temperature rose and their tolerance level rose by a couple of degrees. And there's lots of other more evidence on the ground of seeing that, yes, salmon have been able to adapt and can adapt. There's a great study looking at sockeye in the Fraser, looking at how all these different stocks from different places have adapted to different temperatures through time and are more or less resilient. So there's quite a bit of information out there showing that they are indeed resilient and can adapt.
So are you doing a whole bunch of work that's unnecessary?
Because they're going to adapt and they're all going to be just
They're gonna
fine.
adapt on their own?
Yeah, it's all hunky-dory. Sure, you bet. Great question. And I go back to that first kind of point I put up there, and is that salmon are resilient if the magnitude of change and the rate of change isn't too fast.
Another thing is, are they resilient in that a certain number survive? Obviously, we want stocks to be healthy moving forward. Let's say maybe they survive. They're resilient in that they are still present, but are they resilient in that they have the same numbers as today? That's less likely. If that makes sense. Again, like when we talk about thermal stress, do we put them under thermal stress in this environment and then they move out to the ocean, they have stresses from other things going on? It's this big compounding thing for these fish, and it's another thing we're adding onto their backs, essentially.
What are some of the predation species that are likely to be an increasing threat as water temperatures rise in the global environment?
Good question. I'm not sure about local predators. You probably know better than me as a local fisherman, but in Washington, it's mostly like sculpin are predators, bass, sculpin and bass. I don't know if anyone else has comments on other fish locally.
Yeah, you see like an increase in the squawfish and like other sort of red lots of smolts, as well as bull trout are getting pretty big. That's pretty big on seeing tons of smolts. Again, pretty healthy.
For ocean predators, there are thousands of sea lions in north because apparently because of ocean warming and then laws around cooling them too.
Sure, yeah, marine mammals are another challenge for salmon as well. There's another study recently showing that northern resident orcas in the Gulf of Alaska are targeting Chinook more and more in recent decades as well. So that's, and as their food base changes in the marine environment, right, they may well be turning towards salmon more. Yeah, sea lions as well.
I'm always interested in kind of the long-term or baseline data. And so I noticed a lot of the kind of earliest dates you have for glaciers receding and stream discharge around 1985. So one question is that because of data availability, or is that when things started changing? And then also you say, conditions here are good, we're okay, but were they better in the past? And what kind of data can we look at?
Great question. So for the data availability one for glaciers, yes, it's a data availability thing. So everything goes back to like the mid-80s. It's due to satellite imagery. Our first satellite images were from the late
70s. We really didn't get comprehensive imagery until the 80s. So that's looking at, glacier change since then. And that's why just in the last decade is our first real snapshot of how glaciers globally have changed. We do have air photos that go back to the 40s, sometimes the 30s, but they're a bit patchy. So we can look at a glacier change signal back further in time using other data products. But yeah, that's a data availability thing related to satellite imagery. Excellent question, the second one. Sorry, remind me again, it was with respect to...
You're saying conditions?
Conditions. Yeah, and that's an important point. I didn't say that, like temperature, and if we look at, and again, note that like, this is only data from 2017 and 2016, right? That's a really small snapshot. Is that representative of the recent decade? We don't know. Is that representative of the past? Probably not. That's a good question. Yeah, so I'm optimistic in that 2016 was a pretty warm year and one of the driest years. That tells me that the temperatures that we saw in 2016, they're probably close to a maximum in the present day climate, or at least of the last decade or so. Previous, it was colder and wetter. Yes, some streams definitely would have been better. They would have been a colder regime. Others maybe would have been too cold, less optimal. Dave?
I'm thinking of your graph of the existing rate of rise of stream temperatures in the Skeena watershed. Is there any danger of extrapolating those rates of rise to the 2080 period of time that you had also referenced with respect to glacier melt?
Sorry, you're referring to the kind of last one?
Maybe 4 slides back.
Should be good now.
Yeah.
That one?
That one.
Yeah.
The mountain, the picture of the mountain, okay, I don't know what to describe this, the stream temperatures in that, the 8 colors that you got, including
Yep.
air temperature.
Yep.
What I'm asking is the extrapolation of temperature beyond that into
other drainages.
areas.
Yeah.
How confident are you in extrapolating those data?
Not confident.
So, and the other thing is, this is kind of the Skeena watershed region you're talking about, eh? And you mentioned earlier on that there's an optimum temperature for salmon. Some cold water streams are less optimum than warmer ones. So does this picture mean that since the Skeena watershed is pretty good right now, it'll become less good in the future? Does that mean the conditions would be more optimal further north?
Yes, potentially yes. So first of all, in terms of expanding, so know that this is just Kitsumkalum River. So all the colors here relate to a sub-drainage within the Kitsumkalum. And so taking this and extrapolating it to other neighboring watersheds is problematic, I would say. Part of the reason here, like Goat Creek was a total shocker to me. Why is that so much colder? And so these little local scale impacts that we have on stream temperature are really unknown. So I'm not confident in extrapolating this. But yes, as you go to different watersheds, you may have some that will benefit with temperature rise. So for example, right, so orange, this is Goat Creek, Beaver, and Nelson, these 3 right here, that temperature rise probably gets them into more of an optimal temperature threshold for those subbasins, as with climate warming. We lose the glaciers in those watersheds, they warm up a bit, there's maybe more bioproductivity, salmon production might be better in those. And it'll be similar in other basins where you have more glacier cover, or it's shaded differently, or your mean elevation is different. And all of these factors play in terms of what's the thermal regime of that stream. I don't know if that answers your question.
I'm thinking of optimal regions going further north into Alaska.
Gotcha.
For example.
Yeah. And so, again, it's really spatially variable in terms of where you have glaciers, where you don't have glaciers. There's a lot of study of glaciers around Anchorage showing that there's actually already streams there under some significant thermal stress, even though they're quite a bit further north, watersheds without glaciers. So yes, in general, as we go forth, that image I showed at first, we've got Washington down here, and then us, and then up towards Alaska. In general, as you go further north, you're probably getting into watersheds that could benefit, or at least not be as impacted as greatly.
Is any of this kind of data being used in fisheries management as opposed to just counts of return?
In terms of like specific local management, I don't know. I don't know if anyone here is from DFO, but in terms of like other studies I've read, a lot of the recommendations there are specific management recommendations. Some of them are with respect to understanding where you have these thermal refugia. Where do you have a place that is cold and is a place for salmon to escape from warm water and go to, and to protect those thermal refugia once you identify them. That's one. Another one is identifying temperature sensitive streams in terms of management. So like those you have to have a larger, let's say, riparian buffer for logging, or no logging whatsoever, because we know that logging up to the stream side or near the stream side has a significant impact. So I guess the answer is yes, this information is being used. In terms of how much it is being used on the ground in decision making here in our region, I don't know. Question back there.
And one of the other challenges for fish habitat in some of the rivers will be the physical changes that might come as glaciers retreat and pull the lateral and thermal moraine material, the gravel and rock that's been basically glued to the ice for 10,000 years is now failing because of gravity and water flow, moving its way into the system. And I've seen rivers here that have massive amounts of new gravel mobilizing down the system, which displace fish habitat and displace the whole river into new channels.
Certainly.
Quite unique to
Yep.
Pacific watersheds.
And that's a topic I didn't discuss. I didn't discuss turbidity at all. So the cloudiness of your water, how much silt is in this water, that's a big role. And yeah, that's really critical. As these glaciers recede, the glaciers when they're in place, they buttress all this over-steepened material, this loose rock, gravel, sand. As they recede, they debuttress that and they can then fail into watersheds. Yeah, super critical.
Does your study also measure that?
We have not looked at that yet. No. Charlie.
So I was reading a paper about the Kitsumkalum Watershed and sediment about Atlan, and they were saying that there's a research that's been done regarding sediment on Kitsumkalum.
Oh,
Do
cool.
we have access to this data somewhere?
I'm not familiar with that. Yeah, if you could point me in the right direction, I'll look into it and see. Thanks, Charlie. Other questions?
The early representation, the map of the coastline of the glaciers, with that you suggested the salmon would be moving further north because of the habitat warming south. Thinking about Alaska and wondering whether there's right now a smaller population there that would grow, or would there be an infringement on the population that's there now?
To population of humans or
No,
population
fish.
of fish? In terms of we lose the ice and then there's a
Well, more fish would be moving north
yeah.
to spawn,
Yeah.
I'm assuming. Now, are salmon spawning enough in Alaska now that there would be a struggle for spawning space?
Oh, I see. Interesting question. In terms of my understanding of previous runs and how big they were, my gut reaction would be no. There wouldn't be a struggle for spawning space, but I'm not sure. That's a great question, right? So if you've got, let's say, reduced number of streams that are these thermal refugia, do they then all start to funnel towards them? I don't know, but my hunch would be there wouldn't be an impact.
Is it too cold in those places for them to spawn?
There are definitely places that are not optimal in terms of temperature, but I've seen streams, salmon spawning within half a kilometer of a glacier in ridiculously cold water in the Juneau area. So I would say no.
I noticed on your list at the beginning, you did have ocean acidification as one area you might study. And so I guess, I'm not an expert here at all, but I guess my concern is the ocean is warming quite a bit. There's a lot of acidification. My concern is, are they going to make it up from that problem, even to come in to spawn?
Right, and that's a big question, right? In terms of resilience of salmon, there are all these compounding factors, these not compounding, the additive pressures, right, that come together that impact them, right? Yeah, I think the best, in terms of management within our local watersheds is give them the best chance, realize that they're under stress, and moving forward, that stress is likely to be increased with different thermal stresses and ocean acidification and other things, and to manage for that additive stress, I guess.
Especially ocean acidification with business as usual with respect to emissions and so on.
Yeah, for sure. And I guess as well, especially with the marine environment, these are really big topics that we don't really know a lot about yet in terms of the impact. So in terms of like marine mammal predation or bycatch and overfishing out in the oceans, or the impact of sea surface temperatures, the blob of recent years, right? These are big things that we really don't have a good handle on yet.
NASA, they're kind of studying that, aren't
They are.
they? Yeah.
A lot of folks are. Other questions? Yeah.
What's the summer, you were saying the summer of 2016 had much less snow, I think, than...
Yeah, the snow melted quickly. We had that really warm March, spring, yeah. But in terms of like how much snow there was in the mountains, I'm not familiar with the data right offhand. I think it was average or slightly below average, if I recall correctly.
I remember one of your slides talks about that snow is unusually hot, something like that. It's related to water temperature. And my uncle Bernard's been commercial fishing out of Port Edward for at least 15 years. And that summer, he and his fisherman buddies said that algae was growing much faster on the bottom of their boat. And for the first time in his life, and he knows like the tides and the coast around there like the back of his hand, he said the runoff seemed so much lower than normal that the tide chart was off by a lot. And yeah.
Interesting.
Fishermen felt it was just too much, too low runoff.
Wow, cool. I'd love to chat with him. I don't know if he'd be keen, but
Sure.
awesome. Thank you. Any others? Dave?
You talked about, at the beginning, about the impact on food, and it was kind of a focus, but there wasn't much on that. So I'm wondering about the consequence for food. In the worst case scenario, you're looking at, say, closed pen fisheries or pool fisheries to sustain a food supply as opposed to wild.
Sure, yeah, no, I didn't get into like us being able to maintain ourselves and having, enough calories to consume. I guess my framing with respect to food security is more looking at continuation of, traditional usage of salmon, right? And especially if we're in these conditions where they have multiple pressures and we need to allow them the space to do their thing, we confront things like we have this summer with the potential closure of Chinook and sockeye, right? That may well be more and more common moving forward, or need to be at least entertained moving forward, acknowledging these multiple stresses upon them. And so that dramatically changes the food picture, particularly for people such as Kitsumkalum community members, for both sustenance but also traditional lifestyle, right? And so more and more along those lines. But yes, in terms of getting enough protein, right? The oceans are kind of our breadbasket globally for protein, and we've been dredging them figuratively and literally for many, many years, and that the protein source is going down. And so yeah, in terms of aquaculture, moving maybe towards closed net, onshore aquaculture, that kind of thing, for fish-based or marine-based proteins, maybe.
Let's thank Matt one more time. And I think Bruce is outside with some posters about the coming events. This is our final speaker series of the, no, it's not our final speaker series of the year. Come on, you come and tell us when the next one is.
Yeah, thanks. We will be continuing to have our speaker series at the last Wednesday of the month up until, I think, June. And our next one we'll be combining our public speaker series with our elder in residence and having a discussion about governance in First Nations, from clearing the trees to modern day treaty. Just made that title up. I gotta see what he thinks. So please feel free to join us.
Thanks for coming, and thanks for a great discussion, everyone.
Thanks.